All right, so I think we can start. Okay, so now we have our first invited talk, which is given by Fabio Zanasi from UCL and University of Bologna. And Fabio will talk us about category theory machine learning. So Fabio, please go, the stage is yours.
Thank you. Okay. Yeah, I was saying it's nice to be in front, especially of this audience. I'm used to try to sell category theory to computer scientists or machine learning people, software engineers, but already sold. So that's a different perspective. And in fact, I've been this morning to the talks you gave, and I am afraid my category theory is more like kindergarten category theory to some of you. So it's very simple one, but let's say it's an applied perspective. So it's kind of a means to an end. And that work is indeed about how to apply some methodologies, some perspectives, some techniques from category theory to the analysis of machine learning and what that can bring to our understanding of this field and how can also be useful for people working in that field. This research line, which I've been now working on for the last couple of years, draw inspiration from analogous approaches that me and other people in my community, which broadly speaking, you can think of as the community that you see, for instance, at ACT, at Applied Category Theory. So this it draws inspiration from this series of approaches trying to give a categorical semantics to various kind of component-based systems that arise in different fields of science, and to do so in a kind of a uniform manner. So you will notice many of the systems that are enumerated here, they are expressed as some kind of graphical formalism. And the idea is precisely that traditionally these systems are described in terms of combinatorial techniques, combinatorial methods as graphs, whereas using category theory, we can actually take these graphs and make them into a formal syntax, some kind of algebraic object that we can reason about in a much more powerful way. How that works in a nutshell, let's see just on one of the examples I gave in the previous slide. This, for instance, is a signal flow graph. This is a kind of circuit you find in control theory and engineering to, for instance, model linear dynamical systems. You can think of signal flowing in and passing through some gates that transform it in some way. Now, the idea of this kind of approaches is that this object, which so far is just a graph, becomes actually a formal syntax, which you can express just using a grammar, as you would do with a programming language. And this syntax generates an object, a graphical object, which is the one here on the right, to which we can map our original graph. So if you're used to this kind of reasoning, I can immediately say, when you see here this kind of grammar, what I'm doing is simply to generate a symmetric monoidal category by generators and relations. So these are the, let's say the generating morphisms of the category, and these are the so-called, you may call them structural morphisms. So we have the identity, the symmetries, the empty, and we compose them sequentially and in parallel. Of course, yeah, there are typing concerns that I'm kind of abstracting away, but hopefully you get the idea. So why we do this? Because in here, what we can say about this object is pretty much what we can say in terms of combinatorial reasoning, what we can do about graphs like reachability and the like. What we have on the right here is instead a term of this syntax. So it's actually a string diagram. So it's a morphism in the category generated by this syntax. But now, of course, we can treat it as an algebraic object, study equational properties. Also, from a more practical viewpoint, we can reason about it compositionally. So in this one on the left, if we try to cut it in half, it's a bit unclear how each half, what is the meaning of each half. This is not even a well-formed signal flow graph in the traditional theory. When we go on the right, instead, making such a cut makes perfect sense. We are simply considering a string diagram as the composite of two smaller diagrams, and there is a very simple and elegant way to assign meaning to each of these objects separately as a linear relation, for instance, so a subspace over the reals, and their composite will give us the behavior of the whole system. So this is the compositional reasoning that this kind of analysis enables. Obviously, this is at the very basic level. Then there are many developments you can make on the top of this. So imagine now trying to export this kind of approach, which is essentially the approach of programming language semantics, no? But now generalized to component-based systems. Imagine to try exporting it to the setting of machine learning. Just as in the case studies we just seen, in machine learning, we have many different kinds of graphical formalisms where there are interconnected components. We have to be aware about resources being used, and we have very complicated schemas that we wish to study in a more principled and simple way. Here, what I'm just doing is to throwing at you some kind of different kind of architectures for neural networks, for instance. We have a convolutional neural networks with convolutional layers. We have some reinforcement learning. We have some deep learning, and so on. So what is that we want to say about this system using the techniques we just described? So first of all, as usual, there is a desire for uniformity. Here we have many different algorithms, many different models. Their theory, I wouldn't say is developed somehow independently, but to some extent, of course, as you know, when there is an engineering problem, there is a tendency to develop a solution or a way of thinking that is specific to that problem. Now, obviously, what we want to try to do here is to recast these techniques and new ones into a more systematic, uniform setting where we can think about all these different models in a uniform manner. This leads, in turn, to a desire for better programming principles. Now, obviously, there are many suites that have been developed software for reasoning about machine learning. Think about TensorFlow, PyTorch, and so on. Each one takes their own primitives, no? For what kind of mathematical structures we should use when we reason about machine learning, when we design new algorithms, or when we want to specify their properties. And who says those are the right structures? This is a bit the same thing as in concurrency theory, no? Where it's still kind of unclear what are the right structures we should pick as fundamental. Now, I think category theory gives us good information, good evidence on what kind of structures could be suitable. So this is a kind of research that we want to contribute on. What kind of design principles, what kind of primitives could be good or on which to develop a nice programming environment for machine learning. There are two other issues which are also concerned with how machine learning interfaces with the general public, with society at large. The first one is to do with something called explainability. Here, essentially, the idea is that people use machine learning algorithms in a form or another every day, but usually their interface is very limited. They are given an answer, but they don't know how that answer was computed on the basis of what evidence, what was the line of reasoning that led to it. Think about going to the bank and you want to get a mortgage, a very important decision in your life. And on the other side, you get an accountant that runs your data in a program, and then the program says, no, this person cannot have a mortgage. And they say, why? And they say, well, the computer said so. No, that's the kind of thing that we want to explain. So that's there is a societal concern over there, no, for not only being able to use these systems, but to understand why they reach certain conclusions. Now, my stance, I think our stance as people working in semantics should be that really the semantics is able to inform this kind of reasoning, like is able to inform how these algorithms actually work, what is their mathematical meaning. This also leads to another related but separate issue, which is the one of trustworthiness. We all know very well from for program verification, there are areas of software development in which there is the need for critical systems to be safe, to be trustworthy. There are systems that they shouldn't fail, so we should have kind of some correctness check, some way of proving them to be correct or to specify some other kind of property. And obviously the same applies to machine learning. So there is there is a theory of formal verification that tries to apply to machine learning the same kind of principles and guarantees that we know very well from the theory of programming languages. But this theory is very early stage, and I think a categorical semantics for machine learning could inform it just as well as the categorical semantic of programming languages was able throughout the years to inform formal verification. So this is a bit, let's say, the context, why we are doing this, why it could be interesting for us, but also for the other people. And now I'm going to present, we are going to narrow it down because obviously it's a huge enterprise to try to capture machine learning in general. Machine learning means many things. So let's try to be a bit more convincing and narrow by focusing on a case study. So gradient-based learning is a kind of machine learning that is very simple yet fundamental. It's essentially how neural networks typically are trained. This is a scheme, a little picture presenting how gradient-based learning works. So imagine you have your model, a neural network. So this is a graph with nodes and arcs between them. And you have to imagine the information flows left to right. There are some weights on these arcs, and that express a certain function that the neural network is computing, a function over vectors of real numbers. Now, an input comes in, for instance, a picture, and your neural network is giving an output, usually called a prediction. For instance, we can imagine this network is trying to figure out whether the input is a cat or a dog or another animal. Initially, at different stages, the prediction could be wrong or could be just partially correct. For instance, in this case, it's saying probably it's a cat, but they're not quite sure. So this information is fed into the loss map. The loss map is simply a function that compares the output of the computation with a set of labels. So the labels here are actually the true answers that the machine was supposed to give. And for instance, in this case, the actual answer was that was 100% a cat, what you see in the picture. So the loss map compares this with the prediction and gives back, let's say, usually the difference, but let's say the error that the prediction contained. This is fed into something called an optimizer, which is simply yet another little algorithm that what it does is to change the parameters, so the weights on the arcs, based on the information of what the error was. And this is where the gradient computation happens, which gives the names to the algorithm. And there is yet another parameter, which are the learning rate. And the learning rate is just a parameter telling us how dramatically we should try at each step to change the parameters towards a better algorithm, an algorithm that computes a better answer. So a couple of points. Here we use the labels. This is called supervised learning, where actually there is a set of real answers that are given. There is also unsupervised learning out there, which we leave out of the picture for the moment. But we can also do it if you're curious. Another thing to see here is that, as you can see, there is information flowing in different directions. So there is the function being computed, sort of left to right, and then there is some information flowing back to the net. And this is why this is suggestively called out by me, but it's like how it's actually called backpropagation algorithm most of the time. So this is the gradient-based learning algorithm, very shortly. As you can see, it has lots of moving parts. It has lots of things that do little things, and as theorists, our first impression is, how can I clean this up? How can I try to make this more uniform, more systematic, what principled. What is the semantics of this? No? What kind of mathematical gadgets should be able to model each of these components, and how can I describe their interaction? So said in more elementary terms, what are the fundamental structures that underpin this process of gradient-based learning? So the answer that we came up with in our own approach, then obviously there are many different approaches, is that we are trying now to turn this diagram into this diagram. So at first, it seems that we didn't gain much, but actually they're very different. So this one is just a funny picture with no formal meaning. This one is actually a string diagram in a certain category. So this is going to be a morphism in a certain category. These boxes here are also morphisms. These lines, they witness some kind of composition happening in this category. So what we are going to have at the end of the process here is a fully fledged algebraic object which you can handle in the usual ways that we like. And what are these boxes here? Well, they are something that we are going to call parametric lenses. Okay, if you're familiar with lenses, those lenses there. The main gist is also we just not establish that in machine learning can essentially be expressed in terms of lenses, but we represent them as string diagrams that kind of mirror the information flow happening in the original gradient learning algorithm. And the learning as a whole, the algorithm that is expressed here, will just be reduced to lens composition. So here we really try to operate a reduction of all these different aspects and traits that appear in learning to a single primitive concept, which is the concept of a lens and of lens composition. So this is the primitive we kind of claim, and we claim is good for the semantics. We claim is good also as a programming principle and for other things that we will discover along the way. So this is let's say the roadmap. What we are going to do. Is there any questions so far? Things you're curious about? Okay, if there is no standing issue, let's get on from here. So now what I'm going to do is to define the categorical entities that we're going to use to model this gradient-based algorithm. A parametric lens is a parametric morphism with lens structure. So we decompose this statement. First of all, we have a parametric morphism. Take a category C. We represent morphisms as simply string diagrams F from A to B. A parametric map simply is a map that is parametric in a certain parameter space P. So you can build a category par of C where morphisms from A to B are arrows that goes from P times A to B for a certain parameter space P. When you compose them, you enlarge your parameter space. So, of course, you need the Cartesian product in this category. And you can also have another operation, which is called reparameterization, in which you change your parameter space. So essentially, as you see here, you simply plug a new alpha and q on the top of the original parameter space F. And you convert your q's into p's along the way. Already from this slide, you can see how convenient it is to use string diagrams here, because we are going to separate parameters from inputs and outputs, and later on we are going to add even more interchange of components. And string diagrams really help us keeping separate these components and really see what's going on there in terms of information flow. As for instance here, the parameter space is coming always from top, and the inputs and outputs instead occupy the vertical dimension. The horizontal dimension of the diagram. As a first example of why we want parameters around, a neural network is as an example of a parametric map. Take the category of smooth functions over vectors of the reals. So in this case, a neural network is simply a morphism in this category. You have your weights, they constitute this parameter space P, together with the biases. So the bias is like the nonlinear part of your computation. And instead, the inputs to the outputs mapping is modeled by a morphism that goes from R to N to R to M, where N is the dimension of the inputs, and M is the dimension of the outputs. Of course, this can be made more fine-grained, if you like. Neural networks are known to have layers, and obviously we can account for these layers. As for instance, this network could be the composite of two different parametric maps, one for each layer, and you can make this even more fine-grained if you like. Yes?
What does it mean, smooth?
Differentiable, so differentiable functions. Okay. So the second ingredient that we throw in is the lens structure. So the lens structure is going to account for this ability that neural networks have to feed backwards information in order to change their own definition. A lens, in a nutshell, is a morphism with a reverse mode. If you want to express this idea in categorical terms, you will say that a lens on a category C goes from a pair of objects A prime to BB prime in such a category, and will be a gadget with two morphisms. One is the get map from A to B, so it refers only to the first components in these two pairs. And the second is a put map that goes from A times B prime to A prime. So lenses are older than category theory. They first appear in database theory, but there is an interesting historical survey by, I think, Jules Hedges, and also studies by Valerio De Paiva, tracing this back to the dialectical interpretation. I see you, Fosco, being puzzled. You don't agree with this? No. Ah, okay. Anyways, I was saying lenses are much older than this. They trace back, as I was saying, to the dialectical interpretation, and they have some other ancestors in the history of mathematics and computer science. They've been rediscovered many times. A notable one, not so much time ago, and in computer science, is database theory, where this terminology comes from. So the get map is essentially a map that gets you to access a certain record and extract a value B. And the put map allows you to update a record. So you have your location A, you get a new value, B prime, and you get a new location A prime, okay, defined out of this. And this is also why we use A prime and B prime. In a generic lens, A prime and B prime do not need to have any relationship with A and B. However, in many cases, and also in the case we will study, they do have a relationship. And we use the prime here to pinpoint that this will be a change in A and this will be a change in B. So if you think about a lens as a string diagram, it simply may be something like this, okay, where I say that I have an AA prime and a BB prime. However, this is not very enlightening because it doesn't say anything about the get and the put map, and it doesn't allow us to really describe the information flow, the forward and the backward mode that are instead what the lens is trying to describe, to suggest with its structure. So this is why we use a different string diagrams, class of string diagrams, which are these ones, in which you see the A splits into two. It goes in the get map to get a B, and it goes backwards in the put map together with a B prime to get back an A prime. So this is suggesting that the get map is the forward mode, and the put map is kind of a backward mode. It is suggesting that A are some kind of the inputs, and B are some kind of the outputs. And now you're wondering, what am I doing here? Because I've said all the time, string diagrams are formal entities, they're morphisms in a category. What are we drawing here? In which category do these things live, and how we are even allowed to draw them that way? Well, the answer comes from, let's say, a little detour we can make from the theory of the category lens of C. It turns out that if you take presheaves over lenses, you end up in a category of so-called Tambara modules. This is a category of profunctors. There is a paper by Guillaume Boisseau, which some of you may know, in which he describes essentially this category of Tambara models and how you can express lenses in it. So we all know that any category is a faithful embedded in its own presheaf category. And this is what we are exploiting here. So anytime we have a lens, we can see it through the embedding in its own presheaf category as a Tambara module, and we can access the very nice string diagrammatic language of the bigger category in order to describe it. Now, I'm not going into the details of, let's say, how this category of string diagram is actually defined. You can find this in the paper. I can also give you the reference afterwards. But anyways, this is what we are using here. We are when we use this notation of string diagrams to describe lenses, we are not cheating. We are just using this embedding. So we are still completely formal, but we are able to use a much nicer notion. Yes?
But the product is an arbitrary monoidal product, or that be Cartesian?
So in lenses, it's Cartesian. However, in this theory here, there is also the study of an arbitrary monoidal product. And lenses, when your monoidal product is not necessarily Cartesian, are called optics. And this is the level of generality of the paper I was mentioning. So you can develop that theory. And in our case, the approach I'm describing, we assume the Cartesian product, but I don't think it's really tied to that. I think you could make an effort and generalize it if you want. Okay, so having seen what lenses are in general, let's see our motivating example, how it turns out in this context. So a neural network is a lens in the same category we saw before. How it is defined? Well, this F here is simply the function that the neural network is computing. And what is the update map? That's the most interesting part. That's the so-called reverse derivative of F. So if you the reverse derivative is really the part that is allowing me to compute these parameters. And this reverse derivative of F, the type is the following. It takes inputs in A, it takes a change in the outputs, and it gives me a change in the input. So now you see why I use this prime notation. How is this change in the input computed? Well, it's going to be a linear approximation of what it takes to my original x in order for f of that x to be the original f of x changed by the b prime. Okay, so it's the typical thing you do when you take the reverse derivative of a function. In more formal terms, this J here is the Jacobian matrix that takes the partial derivatives of this f with respect to x multiplied by this y. And also this part that we use in our own approach draws from a nice piece of theory, which is this theory of reverse derivative categories, which is an attempt to axiomatize this notion of a reverse derivative in a categorical setting. And this author studied this operation with this type. And here we simply limit ourselves to observe that if you take a function at this reverse derivative, as defined, for instance, in this paper, they form a lens, which is what interests us here. So now is the time to put this together. We have a category lens of C, and we know how to do para. We do para lens of C. And this will be the category where we study parametric lenses. So amorphism is going to be a parametric lens. So it's something that we depict as a string diagram in this way, where the parameters are above. And you see now that this being a lens, there is always a forward and a backward information flow, but for the inputs, the outputs, and the parameter space. Composition is along the middle part. And we can also do reparametrization, just as we did before. So this is how it looks like, a neural network, if we use the formalism for lenses that we described before. And you can already start seeing how things are gonna get more concrete, because the description we made so far is very high level. It's still hard to grasp at what level we get to see those phenomena that we saw at the beginning where we explained gradient-based learning. This is where we start to see them. So if you unpack the lens that we saw before, you see that in the computation of f, the function that the neural network is computing, it contributes the parameter space P and my original A, this giving me a B. At the same time, I have another device in my network, which is this reverse derivative, which is taking the P and the A, but is also taking a change B prime, and is giving me back some change in the parameter space and in A. So you know that the gradient descent learning is all about changing your parameter space. So here already you can start seeing that types are going to match in the sense that we are going to change the parameter space P using this P prime out of R of F. What about A prime? How do we care about the change in A? Well, for now we don't, but we will come back to that point. Nothing will be wasted here. We also use this at the very end. I also want to say this is like the, say, layer level view, but just as we did before for the neural network as a parametric map, we can make this more fine-grained. So this is, for instance, how a single layer of a neural network will look like as a composition of parametric lenses. We can imagine of having a parametric lens for the linear part, one for the bias, so the nonlinear part, and one for the activation layer. And then we compose all of this together. So it's not just that parametric lenses are able to describe a neural network as a single morphism, but you can actually narrow that down and have a more detailed description. So what we have so far of this picture is essentially this. We have described this component here, the model, okay, with its AA prime, BB prime, and PP prime. Now I want to move to the other components, because of course what we have now is barely half a description of the algorithm. No? We just have our F, our reverse derivatives. There is nothing really telling us how what optimizer, for instance, we use to change the parameters, how the learning rate, the loss map, how they all enter the picture. So we need to model those components as well. And it turns out they are all modeled exactly the same. I would say that's perhaps the thing that surprised us the most. You may think that these different things require different kind of modelizations, but it turns out they are all nothing but different lenses of different types, and their interaction is completely described in terms of some kind of lens operation, which could be composition or reparametrization. So now we move to see the optimizer, which I think is the less trivial part among those that are left. The optimizer is an algorithm that usually tells you, given the error, how do you use it to update your parameters. So this is how you do, for instance, in basic gradient descent. In basic gradient descent, we are going simply to make a sum of the original parameter with the change in the parameters that we want to make. And this is how it looks like in our framework. So it's going to be a lens of type PP to PP prime, where P is our parameter space. So we take this lens and we turn it 90 degrees, and we use it as a reparametrization operation on the top of our model. So remember, our model is spitting out these P primes as a computation resulting from the reverse derivative. These are here using the computation. They are summed using the put map, and they are fed back in here. So this optimizer is really doing the job of updating our parameters the way we like. Now, this wouldn't be very enlightening if we just could do the simple case, but it turns out we can do just as well all kind of more complicated optimizers that people use. People don't just use basic gradient descent. They use other algorithms called, for instance, Adagrad, Adam, Nesterov momentum. Some of them use also states, for instance. They are stateful computations. They are not just computed point by point. It turns out they can all formalize uniformly as different kind of reparameterizations. So for instance, this is Nesterov momentum, just to show you one. As you can see, the parameter space is a bit more complicated because I'm also including the states, some states in the computation. I have some extra parameter gamma that is not important here, but is all part of the Nesterov momentum algorithm I usually specify. And you also notice that the put map is also a bit more complicated than before. So this is the lens that is going to model these other kind of optimizer. And for all these others as well, we have alternative description, and they all fit the same format, essentially. So we have seen models, we have seen optimizers. I would spend now some words on the loss function and the learning rate, which, and no surprise now, they also turn out to be lenses. This is, for instance, the square error loss map, also described as a string diagram. Something you'll notice here is how the parameters turns out to be the labels that give us the actual answer in the supervised learning. So this is the B. This device here, this string diagram, is going to compare these B's with the answers that the algorithm is giving us, this B here. I also give out some B prime, which I don't use. And this is going here, doing nothing. And here, however, there is a non-trivial part of this. This is also a lens of a very simple kind. And this eta here is going to be the learning rate. So the learning rate is also yet another lens of a very trivial kind. As you can see, it has no outputs and no parameters, just some inputs. And this is going to amplify the rate. So this is actually acting as a multiplication of real numbers. So if you simplify this picture, because obviously we are in a category, we can use equational reasoning. So if we simplify these string diagrams, we get these string diagrams which describes what's going on there. So we have the supervised learning giving us some B. We compare it with the actual answer coming from the neural network. We subtract the error, we amplify it by eta, and this is going to be the change B prime. And this is going to inform our P prime, which is going into the optimizer and going back. So you see, all turns out to be the same as the intuitive picture we did before, but now it's formal, and now we actually understand it. So the first reason why I did all this is because I didn't understand machine learning. So I wanted to understand it on my own terms, and I think this gives a more clear picture of what's going on in there. Yes?
I would expect some link with. I would expect some link between the optimizer and the loss block.
Yeah.
Okay.
Yeah, that's a good point, because that's how it works in the standard theory. In the standard theory, the block with the error and the learning rate is tied up in the is presented usually together with the optimizer. But this is something that we discover by doing this, namely that they still interact, but their interaction is mediated by the model. So the interaction still happens, but you can study them as separated formal entities. So I don't know. I would call this more a feature than a bug, let's say.
So it is something that it is in the block model that is not detailed in this picture.
Yes, but it is detailed. If you take the picture with the model I gave before and you put it there, you will see there is a link. That this is also why we use string diagrams. Otherwise, you will never figure out how the link works. So yeah, that's a point. Another point is, for instance, the gradient computation itself, the reverse derivative. You'll notice is not part of the optimizer, as it usually is. The optimizer is defined independently of the way you take changes. For instance, the simple gradient descent was simply a sum, an addition. So the way you do changes is specified in the model. In this case, it's a reverse derivative, but this opens up interesting possibilities. Maybe you want to do changes using something else, the reverse derivatives, and you can here separate concerns. Okay, so we have basically covered all of this. The remaining part I didn't describe is simply a trivial lens that gives us the inputs. You see, we are still not making anything of the change in the inputs, but we'll do something of them in a variation that we'll see of this picture. So last thing I want to say is, how do we put, well, last thing, not completely, but let's say last thing for the main picture I want to say is, how do we put all this together? Because I said the composition describes learning. So how that is actually true? We have described the individual components so far. If you take the whole lens, because obviously a composite of lenses is yet again a lens, this is very simple. It's actually as a parametric lens, so as a morphism in parallel lens of C, is simply a map from 1 to 1 through 1 to 1, because you see there are no inputs and not outputs. However, if now you take parameters into the picture, you see you have a very rich space of parameters that are fed into, which essentially are your inputs, your parameters, and you also keep track of your labels that you use in the supervised training. So if now you unpack this lens, especially the put map, because the get map here is trivial, okay, it's the identity, but the put map here is very rich, is this thing here, and the put map is what is doing all the work. So what is the put map doing? The put map takes the inputs, the parameters of the network, and the labels, and is giving me a change in each of these. So how is this change computed? First of all, I use the f, the actual function that the neural network is computing on my input and parameters, and I get some b, which are the outputs. Then you see this b is used here together with the labels. So BP is the actual output, and BT are the labels that I should compare. And this is taken together with the alpha here is the amplification of the error. So I amplify the error and I compute the loss, which compares BP to BT. I take the reverse derivative of this, and this gives me a change in BT and a change in BP. And finally, I take the reverse derivative of f with my parameters, my A, and the change in the outputs. And this gives me the desired change in the parameters as the first element. So this is a bit maybe hard to follow, but I just wanted to pattern match the types of these morphisms to show you really how the actual algorithm that is typically used to gradient descent arises from this put map completely. Of course, learning doesn't resolve in a single iteration of this algorithm. Usually you do an iteration of it. You iterate it many times. And this is how you can do it. For instance, you can think of your A and B as your data set. This becomes, in this view, they become the parameters of your algorithm. And the P's that here are parameters, they become input and output. So you have your put map, and you keep applying it to your P's, taking the A and B, the data set as parameters, and this will transform the parameters as many times you like, and as a result, you will have the parameters to use in the trained network. So this is how the training would work if we would imagine it as an iterative process, how it happens in actual real life. It's interesting in this picture compared to this that in here, the parameters and the inputs outputs switch roles when it comes to this training process, which in a sense is reasonable, no? Because if you think about machine learning, the real protagonists are the parameters, no? That needs to evolve, and the inputs and the labels are just used as extra ingredients that you use in this learning process. Okay, so let's say we are now done with the generic picture I wanted to present. I want to conclude by showing a couple of variations. So the first variation is something called deep dreaming. Well, let me first say why we want some variations, because the point of doing this abstraction of category theory, of taking all the trouble to recast things in a different setting, is not to just model a specific context, is also to show how it allows us to model different contexts in the same manner or to discover new ones. So the first variation is in the category of modeling other contexts that are known. This is something that people in machine learning literature call deep dreaming. What it amounts to is a trained neural network that takes an input image and changes it according to its bias. So for instance, imagine your network is trained to recognize dogs. So you can think of your network as something taking a picture of jellyfishes and morphing the image until you get some psychedelic dogs over here, okay? This is your over-processed image. This is something that people study. Don't ask me why, but it is a thing. Well, it turns out that we can straight away give a neat description of what's going on in deep dreaming. It just amounts to shifting the optimizer from a box over the model to a reparameterization to another box over the set of inputs. And there is really when we make use of this A prime. So the change in the input is not important in the model, but at the moment we want to reprocess our input image, which is what happens in deep dreaming, for instance, we can think of this reprocessing as the act of giving this change back to an optimizer that is feeding me a new set of inputs. So deep dreaming is nothing but shifting this optimizer box over my inputs and their changes. And you see now my model is assumed to be trained, so I'm not doing anything more with my P primes. Second variation I want to mention is learning in other categories. If you were following, you'll notice what we did is not strictly related to smooth functions or to real numbers. No, we made some assumptions along the way, but these assumptions also hold in other categories. Essentially, we need a Cartesian structure, the structure of a reverse derivative of some kind, of some change. It turns out another category of interest that satisfies this assumption is Boole, which is the category of Boolean functions, which have an operational model in Boolean circuits. So this is a Boolean circuit. In terms of learning, we can see a Boolean circuit as a very simple kind of a neural network, where instead of having real values flowing in and out, I'm just computing with Boolean values, with bits 0 and 1. So we can just take our picture of learning for neural networks, transfer it to the category of parametric lenses in Boole, and try to see what happens. Does it make sense to learn Boolean circuits? You notice that we're using basic gradient descent. Everything else looks the same. The only difference is we are taking a Boolean circuit as a model. The values flowing are now Boolean values. And another interesting aspect is that for the model here, we actually have a description of our F in terms of a circuit syntax that is given to us. Because Boolean circuits have a tradition of being studied in terms of string diagrams. There is a grammar developed in the French tradition, the works of Yves Lafont, Buroni, and other people that study Boolean circuits in this syntactic way. So this we can use to specify our F, and it turns out the reverse derivative can be defined compositionally with respect to that syntax, which I find quite interesting because, as you can imagine, doing it compositionally may lead to some scalability in computing these derivatives, which of course is an expensive process. So this is some highlights of the Boolean model. It turns out it makes actually sense to train with Boolean circuits. We know because we took this and implemented it and tried to learn some data set using Boolean circuits. And the thing was actually learning on this data set. There is some developments there that I will mention in a moment. So I've showed you this picture in general, this lens theoretic approach to this gradient-based algorithm. I've seen two variations as just an example of the kind of variations you can do from the basic picture. What are the benefits? Let's try to come back to what we claim at the beginning as things we like about category theory. So we reach some level of uniformity. All components at work were reduced to a primitive concept, the one of parametric lens, which we identified. We managed to abstract different kind of gadgets, devices, techniques, models, and so on. In terms of this concept, in particular, we covered different optimizer, different models, Boolean and neural networks, also different loss maps, which we didn't cover, but like, for instance, are in the papers if you want to look at. They are all instances of the same picture. Another point is, of course, compositional reasoning. What we did here is to divide the whole of the learning algorithm into simpler components, which we can now chop and rearrange differently. For instance, we may imagine of composing two optimizers. For instance, Nesterov momentum you can think of as a composite of Nesterov and momentum, or we can create new ones by this composition. We can consider the composition of a train together with an untrained model. We can think also of plugging the optimizer in here. There is some direction in meta learning which is called training gradient descent by gradient descent, if any of you is familiar, which means you develop your optimizer using another optimizer. We obviously can do it here. We simply use the optimizer as a lens, as a parametric lens. So there is lots of space there for interesting design choices, which can be done at a very high level compared to the usual engineering practice. Another point I want to make is that because we are using string diagrams, we've been perfectly fine using another kind of syntax or types or logic, which you may like more. But I like string diagrams, and the reason is that you can really see how information is now flowing inside your categorical morphism, where things are going and how they participate and interact with each other. So I think this really is a kind of enlightening way of reasoning about this kind of component-based systems. It has proven itself in other contexts. I think also in machine learning it has merits. So just a few directions going forward. I said I would come back to Boolean circuits. So this is a direction that I am currently interested in. There is a trade-off between learning in a neural network and learning over a Boolean circuit. So the neural network has good performances and is not, sorry, it is very accurate, but has worse performances because obviously it's computing over the real numbers. This is to be compared with a Boolean circuit, which has great performances because it's computing the reals, but is less accurate because, of course, the level of precision is not the same as if you're considering a range of real numbers. So there is a trade-off between these two models. There are studies in machine learning of something called binarization, which essentially means to take a trained neural network, binarize it, take a Boolean circuit, and use that. What we can do now is we don't need to binarize. We can train the circuit itself, which is kind of an advancement. And we can even consider intermediate models. So just as the category of Boolean circuits meets the axioms that you need to do this gradient learning, also categories of circuits over polynomial rings meets these same requirements. So we can also think about an intermediate for some middle way through these two parameters. So some family of polynomial circuits that have good performances, but still good accuracy. And this is the kind of field we are currently working on, and especially in something called saturating arithmetic. So this is kind of a middle ground in terms of learning desiderata between neural networks and Boolean circuits. Another point is about programming principles. I said maybe this thing with category theory also give us some interesting idea for libraries, for things to program with when it comes to machine learning. So here are a couple of pointers of tools, prototypes, proof of concepts we developed with these papers we wrote about this. They're not very developed, so don't keep your expectation low, but at least they give some good idea of how they could become something developed. So this is an example using these libraries. These are Python libraries. This is, for instance, modeling a layer of a neural network. So you see this operation here is simply the composite, the categorical composite of these lenses. And this definition of a layer is simply the composite of three lenses. And similarly, when we do the gradient descent, we can imagine we have a method which applies the update to the basic gradient descent in our network and composes it with the loss and the learning rate. So this is just mirroring this picture here that we had, in which we were seeing the learning as the composite of lenses. This is something you can also do as a programming practice, and it's very different from what you do normally. You would not compose functions in order to do learning, but here you can do so. So this thing here suggests a functional style of programming with neural networks, which I think could be interesting and worth investigating further. Last point I want to make is about formal verification, coming back to the last point I made at the beginning about trustworthiness. So there is a whole area called continuous verification of neural networks, which essentially is interested in robustness properties of neural networks, so resistance to adversarial attacks. And what happens in there is that you break the training cycle by at each step of the training verified how are you doing with respect to a certain property, which for instance can be robustness. So how you encapsulate, how you describe the property you're interested in? Well, usually the people in that field use the loss function, and they use a specification language to describe this loss function. So they need different kind of layers to describe this thing. I think that if you use lenses, you are much better off, because first of all, this cycle here, it cries for a formalization in terms of lenses, because there is clearly a forward and a backward mode in this verify and retrain cycle. But I'm pretty sure some of you will see here an adjunction, abstract interpretation. There is lots here to be investigated in with our technology. Another point is also the specification language. We can do better, I think, because instead of having a layer, an overlay over our loss functions, we can let the loss functions be the specification language itself. At the end of the day, lenses are a rich formalism with many operations available. Loss functions are lenses. Let's use them as our specification language instead of coming up with a different logic to work on them. So that's the last direction I wanted to point. I will leave you to some pointers to implementations and some papers from which I've drawn this talk. Thanks.
All right, thank you, Fabio. So we have time for a couple of questions. Okay.
Thanks for your talk. I'll try to make them as brief as possible. The first one is, could you give me a little bit of perspective in terms of what are the contributions that thinking in terms of compositionality and lenses bring to, on the one hand, say modeling. So for instance, what does it add to the TensorFlow graph ecosystem, for instance? And secondly, you mentioned explainability. What's the, let's say, added value with respect to usual techniques like sensitivity analysis or these kind of things? Can we gain something more with respect to what doesn't use lenses?
So for your first question, I think this is basically suggesting different programming constructs that are typical than those that are typically used in TensorFlow. So to make some kind of analogy, I see TensorFlow more as imperative style of reasoning about these neural networks algorithms, where you have this tensor and transformation over them. Whereas in here, you focus more on processes that happen. So in a sense, I would say this is more functional style, whereas I see the primitives that TensorFlow gives you is more imperative style kind of language. And I think these can be very well integrated in TensorFlow. These, at the end of the day, are Python libraries. So it could offer simply other primitives to TensorFlow to design neural network algorithms, which I think can be more succinct. They can hide some of the complexity at times, which of course sometimes is desirable, sometimes is not, but it can have its merits. And I think this goes in a line of research that I've seen recently, about having functional programming to do automatic differentiation, for instance, to do various kinds of machine learning techniques. I think that is the same kind of spirit, more or less. We don't have yet, let's say, a implementation, a library that could compete with the TensorFlow thing, but I think this could be something to be looked into. And coming to the second question, in the explainability context, so I don't think at the present time this gives a really concrete case study for explainability. The idea is more that if you design your models, your algorithms using this kind of principles, is much easier to control how they are working, because you have these modules. So essentially, you have your work architecture is split into smaller parts. You can see the information flowing from each other. You can probably debug it more easily. So that's a bit of the advantage I see. So it's more like, let's say, from the design end of things. It's not something you can really apply when your model has been already built.
But I mean, in terms of, like, if we think of just a feed-forward neural network, the graph is super simple, and all the explainability is in the the way the training happens, right? That's the thing that's hard to explain some of the final results. So can you go beyond just representing the graph?
No, but this doesn't only represent the graph. This represents the training itself. So the training becomes the composition. So these various models, these various models, they are not just parts of the neural network. Some of them are actually, so they express the whole algorithm. There is nothing beyond that. They are the algorithm. So the algorithm, they become part, if you like, they become an extension of your network. Your network becomes not, your training is actually, I say, your network communicating with other networks, if you like. Each of them deputed to for instance, doing the optimization process or so on. So that's the way I see it. As I'm saying, is not yet, let's say, something that I can say gives a convincing answer to some of the explainability issues, but I think can be something that is useful to inform some of those approaches, especially those that look more at the design end of the training algorithms rather than the analysis of algorithms that already exist.
Other questions?
Thank you very much for the talk. I wanted to ask, so I know Bruno is very interested in this question, and I am too, but I never had your side of the picture. So your paper is called Categorical Foundation of Gradient-Based Learning because the things you showed us represent neural networks, but there are things in those categories that are non-neural networks, right? Do you have any idea how you could restrict this framework to capture exactly neural networks? So things where you have like matrix multiplying a vector, nonlinearity, bias, and let's go.
So yeah, something that I didn't mention, but definitely you can do, is to give a presentation by generators and relations to neural networks inside the category of smooth functions. So if you think about Boolean circuits, it's the same thing. You have this syntax that I showed before by this one. This syntax, okay, which tells you precisely what are the Boolean circuits. They're just the morphisms generated by these generating morphisms, okay? And you can do the same with neural networks. You can imagine of having some generating morphisms, and the neural networks are precisely the generated morphisms in this category. So the category, so some people smooth function somehow coincide, and of course you have maybe different neural network representing the same function. What I think at the end of the day is you can use the generating morphism to represent morphism instead inside the category of smooth functions, and this will capture precisely your neural networks. And then it could be interesting to study, let's say, equivalencies, because some neural networks, they do represent the same function, for instance. So that's something that is doable. I don't think it's done precisely or systematically anywhere, but I don't think it's too hard to do. And if you want a hint of how it's done, there is, for instance, a sketch in this paper called Backprop as a Functor. And they do it there somehow. I think that can be expanded into something that looks like that.
Okay, thank you.
Okay, so let us thank again Fabio.
Thank you.